Hello everyone, my name is Yixing Lin. Today I'm going to present the topic of reinforcement learning-based electricity price controller. Why do we need to apply RL to electricity price? What is this? I believe most of us know that global warming is an urgent issue nowadays. One of the main causes of global warming and climate change is the high growth of electricity demand. According to statistics, 20% of the installed capacity of electricity generation is used in the peak time, which only accounts for 5% of the total time. This results in a waste of installation. Therefore, there are several methods um, turns out to control the price for demand response, which can help reduce the demand peak, such as area control error and abbreviation for ACE, and fuzzy interpolation. However, these approaches require prior information about the electricity market, which means that we need to know the parameters about the market beforehand. These are some the drawbacks for a model-based approach for designing a pricing scheme, since the scheme will become regional and lacking of elasticity, and time consuming because we need to have abundant analysis to know these parameters. And the second drawback is that um, due to the rise of renewable energy in recent years, there are more uncertainty in electricity grids. Thus, we need to have a more fast and agile energy balance. Here comes in the reinforcement learning. Reinforcement learning is based on the interaction between an agent and an environment. The environment sends information about the system state to the agent, and then the agent chooses an action in response to the state to the environment. Then it will receive a reward according to the environment by the state transition. The agent learns to maximize the cumulative reward during this repetitive interaction. With appropriate design, it can learn to adapt to different environments, which is our goal, that we don't need to know the prior information about the market model and can adapt to different market environmental change. Second, we are going to talk about our system model. Our system model consists of three parts: service provider, utility supplier, and electricity consumer. In each time slot, the service provider will buy the electricity from the supplier and sell it to the consumer. It then sets the dynamic price in order to balance the supply and demand. Formula 1 represents our system dynamics. PG means the power generation and PD means the power demand. At here, tau G and tau D represent the time constants for supplier and consumer to react. BG plus CG times PG is the marginal cost, and the other hand, BD plus CD times PD is the marginal benefit. Here, lambda represents the price, and delta means the power generation from renewable energy. ET is the stored energy level in the time slot T. Therefore, the system dynamics in 1 can be further expressed as 3 by taking the derivative. Then we are going to convert the continuous model into a discrete time model by multiplying both sides by E, and then we are going to have formula 6, which is going to be our discrete time dynamics. Given 6, the goal of our model is to balance the supply and demand while keeping the stored energy level at a threshold for emergency operation. Next, we are going to talk about how do we apply RL into price control. Figure 2 is a flowchart of our proposed price control scheme. There are three parts: policy, value function, and environment. First, environment will consider the action and the state from the agent to produce the according reward. Then this reward will be provided to the critic to determine the value function. The temporal difference error will be produced by the difference of expected value function and our current value function. This error will be used for actor to determine the policy. The policy is going to be that it's going to help the agents to determine what action it's going to take according to its state to minimize the difference of expected value function and the current value function and to increase the reward. Here, value function, we use tile coding to produce. For further information, you can see our thesis. For action, which is the electricity price, since our action space is very large and continuous, we use Gaussian function to parameterize the policy according to this formula. Third, our reward. We set this formula to our reward because we want to minimize the power generation and power demand and minimize the energy storage. From the first term, if the PG is close to PD, which means the difference is small, then the reward will increase. For the second term, if the stored energy level is close to 1, it will increase the reward. Here we put 1 instead of 0 because we need to have an additional consideration for emergency operation. If the power supply suddenly drops, the stored energy can be used to make up for deficiency. Next, we are going to present our simulation results. Can RL be adapted to changes of different market model as our assumption? Here, our benchmark, we use the real data from PJM area according to the PJM websites. These are the different types of energy production and renewable energy production. And the produced power is in megawatts. This is the result of our actor critic method. Here we can see the most important two line is the green line, RES plus non-RES power generation, and this brown dash line, power demand. If the green line and brown line meet each other, means that the power demand and power supply has reached the balance. So here we can see the results turn out that after T equals to 1800, it's going to have the balance. Next, we are going to evaluate some market parameters to verify that our assumption. We make some difference in our parameters. First, we change the supply cost from k equals to 3 to k equals to 1, which means that the supplier cost is increased when k is smaller. So we can see from figure A that the time for power generation and demand to reach balance is longer than the 1800. Instead, it's now become 3000 time slot. And the second thing we change is the market scale. We reduce both power supply and demand by 1/10, so that you can see our initial value is smaller than before. and it also reached balance at about T equals to 3000. The third thing we change is the RES to non-RES power supply ratio. We increased it by 15%, and the time it reached balance is shorter than before. And the fourth thing we change is the update time span, which means that if we update the power supply and power demand to the service provider, and we can change the electricity price in a shorter time, we can have a shorter time balance. Last but not least, we are going to conclude what we have done and the future work we can do in this area. All in all, we proved that RL actor critic method can be applied to design a more robust electricity price controller in order to reduce the power peak. We proved that it can adapt to future changes under certain range, and we changed the parameters such as different supplier cost, renewable ratios, market scales, and update time span. There are some future works includes we can extend to multi-participant power market and the further optimization of the hyperparameter of RL model. Thank you.